This is All Things Ansys, a podcast from the technical support staff at PADT. Episode 49, we talk with PADT's lead CFD engineer, Clinton Smith, about the different ways you can model pollution with Ansys tools, followed by news and events in the Ansys and PADT worlds. Hi there, I'm Eric Miller, one of the owners of PADT and your host for this podcast. Here we are at episode number 49, one more, and we hit the big 5-0. I hope that doesn't hit me personally as hard as my 50th birthday did. I think I'm still in depression from that. So it should be a good celebration, and we hope you join us for that episode and what comes for the next 50. We've had 14,545 downloads as of Saturday night. Right now I'm recording this on October 19th in the evening. So, I think if all things go well, by the time we put that 50th one out there and it's been downloaded a few times, we'll have over 15,000 listens to our podcast. I like round numbers, so it'll be nice to have 15,000 at 50. Don't forget to share it with other people. Get the word out there. Let people know that you like this podcast and they should listen to it so we can get more listeners. So today we have a great topic that I enjoyed learning more about. I got on a call with Clinton Smith, who works here at PADT, to talk about the use of Ansys simulation tools to predict and control environmental pollution in the air, water, and he reminded me even sound. It's a really unique and interesting application that uses a wide variety of the simulation capabilities we have in the Ansys suite. So do listen in. It's a pretty good discussion, and hopefully it'll give you an idea of what you can do with the tool. Our lead engineer in the CFD area of the company. Hi, Clinton.
Hi, Eric. How are you today?
Doing good. Thanks for joining me. We're talking like we're very distant, but we're about 10 feet apart. But the sound quality is better when we sit in our offices and use our headphones. So thanks for joining me. We're going to talk today about what we call the ability in Ansys Fluent to do environmental pollution modeling. And we talked a little bit before we started recording. And correct me if I get this wrong. So what we're looking at here is wanting to model. Oftentimes, the goal of an engineering project that's using fluid flow is something is producing stuff we don't want, and we want to understand how much is being produced, what is being produced, where it's going, and hopefully how we can capture it or eliminate it or filter it or something like that. And we can now they've kind of put together a group of tools in Fluent to help us do that. Is that a good statement for what we're talking about?
Yes, that's exactly right.
Cool. And the other thing that I kind of got after talking to Clinton a little bit in the beginning and kind of as a preamble is this is not really any different in some ways than any other multi-species simulation. We're just kind of focusing on the idea of the unwanted species and how to deal with them and to be more efficient in that process.
Yep.
Mm-hmm. So why don't you just kind of give us an overview, Clinton, of what you can do with this tool, these tools in Fluent, and how they kind of work. Maybe even like a workflow for a simple simulation of, I don't know, whatever you want to pick, like combustion or something.
Sure. So from an overview standpoint, with what we're able to do inside the Ansys framework, particularly in Fluent, as Eric mentioned, we can essentially model and calculate the effects of air pollution, which can take on various forms. One of the most common ones is pollution control from a combustion process, whether it's propulsion like a turbine engine or your car, or it could be some type of industrial combustion process. And particularly, we're looking at what pollutants form. So we're trying to predict, nitric oxides formation, sulfuric oxides, or even soot, depending on what it is. And we're always striving for greater accuracy there. Because the regulatory requirements are always getting more stringent, and of course it's bad anyway. So we want to reduce those things as best we can. And so that's kind of the air pollution arena, and then we can also predict effects of water pollution, which again is a huge problem, as everyone is pretty well aware. Treating wastewater, cleaning up oil spills, these types of sort of negative situations, we can actually model and approximate what happens, and then find ways to maybe mitigate it, whether that's in treatment plants or cleanup strategies for oil spills, and so on. And then last, but definitely not least, is the idea of noise pollution. So predicting sound, whether that's due to flow-induced sound or device-induced sound. But increasingly, it's becoming more and more of something that people designing devices are becoming more and more aware of. And sound can be, if something has a really irksome or frustrating sound at the proper frequency, it can drive you absolutely crazy, and you wouldn't buy it or you wouldn't go there. Right. So that can be also, we can approximate the effect of sound in a medium, typically air.
I'm glad you brought that up. I was at a conference 2 days ago, and one of the sub-sessions was on drones. And someone asked the question of the expert from Intel, actually. They've got a big drone program. Why aren't commercial drones doing better? And was it cost? Was it regulation? He said it's noise. They're really loud. And every time there's the privacy concerns, but what's really stopping it is the noise pollution they create. If you had these things buzzing around, it would drive everybody insane. So we need to reach out to those of you making drones and use this package to reduce the sound signature as well, the sound pollution. I didn't even think about that. Yeah,
that's pretty fascinating. Makes sense.
Yeah, it was kind of a surprise because I thought they were going to say it was the privacy issue, which a lot of people have. They don't want these things flying over their backyard while they're lounging by the pool. But you can route them down public streets, but nobody wants to hear them. So it would be really annoying. So great. So why don't you explain? I don't know let's start with the water pollution. I think that's pretty simple, and I think Nathan was working on a project for a customer where we were introducing some waste material into flow, and then predicting what it looked like downstream. So why don't you just kind of explain what that kind of a simulation would look like from as far as introducing the pollutant and tracking the pollutant and maybe putting in some mitigation.
Sure. So a common one are modeling like municipal, what we would call waterworks, canals or channels or water controlled ditch systems with gates, and often those are feeding into they're redirecting clean water out from the sanitation plant, or they're bringing the dirty water in to be cleaned. And so in situations like that, we would model those waterworks, shall we say, with maybe some initial concentration of particulate matter, whether it's like a sewage type of pollution, or maybe it's a chemical like chlorine or ozone that where we have sort of in solution. We would typically say we have some guess of what we think it is based on a measurement, perhaps from the municipality. And then we introduce that into our Fluent model, and we basically let the model show us where does the sewage particulates migrate to under these operating conditions. Yeah. So and I think the issue there was going through some weirs or some gates. They were worried about concentration in the turbulent area, like a whirlpool or something like that, if I remember correctly. Exactly. Yeah. You're looking for where the dead space is, where does the flow sort of settle out, or where does the sludge concentration build up, and then there's other concerns as well. Once you get it into your sanitation plant, what do you do with it? So you have big flotation machines that where you have a flotation machine is basically just a big tank with an impeller, some sort of impeller in the middle, and that we can model the motion if we want to get that detailed of that giant, in some cases very large boom impeller that moves slowly around, basically mixes the tank for some purpose of floating waste material to the top. They bond it with a chemical, and stirring it up makes the bonding work. And then you get the bad stuff to float up to the top, and you get everything else to settle out the bottom. And then you take the water and go downstream and do it again. And so you sort of clean it, multiple steps through these flotation machines. And we've modeled those here at PADT before. They're used for water processing and lots of other applications. So let's dig into that a little bit as far as the mechanics and the tools available to users.
we can model that chemical. How would you model the chemical bonding? I introduce a chemical that changes the buoyancy of a certain pollutant I want to remove. How's that modeled in Fluent?
So it's like many things. There's sort of a variety of ways you could do it. So we can model the full physics if we want to. We don't do the molecular scale dynamics necessarily, but we can model the chemical surface reaction of, say, the flocculation agent, which is basically just think of it like dish soap.
Okay.
Right. You put your sort of sticky flocculant into the material, and you can model that bonding onto your chunk of particulate.
We won't talk about what it is. Yeah.
Whatever it may be. In mining, it's like a piece of rock, right? Or they use these in paper processing, so it might be a chunk of paper.
Okay.
We can take that and model the surface reaction of the dish soap, the flocculant chemical, and then say what happens. And that's the most rigorous way. But that's pretty detailed and can sometimes be a little more costly. So we could take a step back and just say, hey, we know something about that because we've either studied in a lab or we know the physics or whatever it may be, and we can just approximate that and say, well, we know this happens. We're going to say that we've assumed it's happened already, and we're going to create these particles that have the characteristics of the flocculant bonded to whatever it is already.
Okay.
So, and then just let that float to the top. And how does it float to the top? And how does the water currents and the eddies change that or make it better or worse?
Cool. So you can really dial it in up or down the fidelity you want of those different chemical or physical reactions. Yeah.
Yep, exactly.
Cool. Very cool. Okay, well, let's step it up a little bit into combustion, which is what I thought of when we first brought this topic up, of course, and we've got an internal combustion engine project that we're applying this to. We're not just looking at the efficiency of this cycle and the internal combustion, which I can't talk about in any detail, but we're looking at not just the efficiency, but also the pollutants that are created in that reaction. So what are the tools available on the combustion modeling side to calculate what's created by the combustion?
Yes, so there's several tools available. Kind of the classic example is like jet engine combustion or internal combustion, IC engine, either diesel or gasoline. And in those two scenarios, we have physics models available to calculate the full reaction physics. So what actually happens when you burn the fuel, and what does the flame shape look like, and what reactants come into the process, what products do you get out of it? And then from there, that's really where we start to get interested about the pollutants, because the pollutants are just products that come out of it. And we can then say, under these conditions, we can ask Fluent to tell us, how much NOx, nitrous oxide, do I get from this part of the process, or how much sulfuric oxides do I get from that part of the process? What type of free radicals am I getting coming out of the reaction? Am I getting, just a hydrogen ion bouncing around that might bond to stuff, or maybe an oxygen ion that's been stripped off of the water that was somehow part of the initial reaction? Again, that's bouncing around that could oxidize onto something and cause problems. So we can then say, at these operating conditions, these are the types of pollutants that I get, and then from there we can predict the time evolution of those pollutants through the system.
Through the system itself. Very cool. And again, it's different levels, right? You can get to the point where you're writing actual code to model these reactions, use some expressions, or even some pre-existing models that you can just turn on. Is that valid?
Correct. Yeah, most of this is built into the code. It's been developed significantly since even the early days of Fluent and CFX. So They do. They both have and other codes as well. So we have the reaction design suite of tools that also have the ability to predict NOx formation, sulfuric oxides, CO. So these tools have been developed over probably 30 years or plus.
Right.
And so essentially now from a user standpoint, in many cases, it's as simple as just checking the box on once you've done your combustion reaction. Now, if you have something unique, maybe that hasn't been done yet, of course, you can always customize it. You can use expressions. So you can write, a simple linear relationship as an expression between, say, one variable of your system and another, and then just type that in, in human readable syntax into a field and see if X are fluent. Or, if you have something that's a bit more unique, shall we say, from a mathematical standpoint, where maybe it's nonlinear or it's highly time dependent, you can tie that more directly into the solver, and that does require some coding.
Right, but it's all there, and you can use the level that you need to get where you need to go, which is pretty exciting. So we talked about the creation of the species that we don't like, so we label them pollutants. How about modeling getting rid of them? We talked about flotation, but what are the other mechanisms that we can model in the tool set? Yeah.
So that kind of brings us to some other types of processes, like basically air quality control.
Right.
That's kind of a broad category. So in some cases, we have like a catalytic converter in your car is a good example, where we can model again, a variety of ways. We can model the detailed physics of that device and the bonding of the pollutants to the catalytic filter material. But often what we end up typically doing is we approximate that and we model the blockage, because when you're typically, as a car truck designer, you want as little blockage as possible to get as much horsepower as you can. So you want to minimize that, but still scrub out all the bad stuff. So then that applies in other applications as well. So we can model other types of air scrubbers that are used pretty widely, like in industrial processes. They use electrostatic precipitators a lot for scrubbing dirt. You can take dirt out of the air. You can take other types of like concrete dust. They're used. And you push the flow through some big plenum and you react, you have a charge differential, potential difference.
Cool.
Through some plates, just almost like a battery, but it's air flowing through, not a liquid catalytic material. And you basically use that charge differential to attract the dust or the cement or whatever it is you're scrubbing out of the air onto the filter grids. And that's something we've done at PADT and helped others do as well. So that's also possible. And then there's other types of devices that are even more complex, like selective catalytic reduction is a scrubber for diesel processes. And that uses other types of physics, and we can model those also.
Very cool. So it's pretty broad application, both in the creation and the mitigation and prediction of where things are traveling. Is there anything else that people that are interested in modeling this kind of stuff should know about the Ansys tool set for this area?
Yeah, a couple of things I would add. I mentioned briefly at the beginning, but the ability to model the effect of oil spills, which are maybe a lot less common than, say, wastewater treatment, but they are, of course, very terrible when they happen.
It makes a big impact when it does happen.
Exactly. Yeah, and of course, the oil industry operators have to model this stuff because they have to prove that to the regulators that, hey, we're not going to blow up this pipeline and it's not going to fatigue out and leak oil in the Gulf, or the ship's not going to crash and leak liquid natural gas, whatever it is. So they do a lot of a priori modeling of trying to predict what might happen if there's this failure mode, whether the oil slick's migrating on the ocean surface, whether it's like in the deep water case, it's shooting up deep under the ocean. We have that ability as well to say, here's this whatever it is crude in some place, and how is it going to evolve over time in the ocean or in this river or whatever it may be.
Cool.
And then last but not least is the noise pollution. I'll just touch on that real quick.
Yeah.
There's lots of cases that we find in life and in designing products for this, but like drones, of course, is a perfect one. But even like your AC system in your house, if you have certain conditions, it can whistle if you have the filter in wrong or whatever, and so we can simulate that. Again, it's a CFD calculation of the flow, but then what we're really looking for are the tiny pressure fluctuations that actually represent the sound. And we can interrogate the solution essentially and say, at this operating condition, what does it sound like? How bad is it? What's the frequency? What's the pitch? And so on and so forth.
That's very useful. Yeah, cool. So, I'm sitting here thinking about it, and, a lot of what we do as engineers is we design products to specifications and requirements, right? And stuff we don't want from what we're doing is just as important sometimes as maximizing the efficiency of getting the stuff we want. And these are some great tools to allow us to design to those requirements, to minimize or handle or sequester the things that we produce that we don't want. So it's pretty cool to think of it that way.
Exactly.
Yeah. Well, I really appreciate it. I actually learned a ton, and it's I haven't really thought about it this way ever. So I'm glad this came up. I just think of Fluent as modeling fluid flow and reactions and all those things, and I sometimes don't think about the class of applications. So this is a good one. Yeah.
Yeah, it's pretty fascinating stuff. And then the tools are getting better and better. And of course, computers are getting faster and faster. So we can do things even we couldn't do 5 years ago with the tools. So it's a pretty fun thing to be a part of.
That's a great way to finish it, because I think some of us that have been in the industry for a long time would look at modeling these situations and go, it's a lot easier to test. There's just no way I can predict this behavior, but that's not true any longer. Or maybe there's no way, but it's going to be really complicated. The computers have gotten faster, the software's gotten better, the models have gotten more accurate. So if you haven't looked at this in a while, it's probably a good time to sit down and take a look.
Exactly.
Cool. Well, thank you, Clinton. You're going to be talking about this more in a webinar coming up. When is that?
I believe let me check the calendar.
Yeah, I'm doing
it's
the same
coming
thing.
Soon. I think it might be next week, but let me just, I don't want to speak out of turn here.
Yeah.
Yes, it's the 23rd. October 23rd, Wednesday at 11 a.m. Pacific time.
Cool. So do attend. As we always say, we like to talk about this stuff, but when we do the webinar, there's real examples with pictures, so it's a little bit easier. Hopefully we piqued your interest in signing up for that webinar, and as always, you can watch it afterwards as well. You just need to register and download the recording. So thank you, Clinton. I really appreciate it. I know you're super, super busy, so thanks for taking the time out to do this. And I'm going to drive by the SRP. SRP is one of the local power suppliers here in town, but the SRP plant that I drive by on my way home with a slightly different point of view. I'm going to see streamlines coming out of those stacks now when I go by with different colors for particulate concentration.
That's right. Well, you're welcome, Eric. Thanks for inviting me. Great to be a part of it.
Talk to you soon. Thanks.
All right. Bye.
So I very much enjoyed that, and we'll drop in on his seminar if I have time, which, as we mentioned, will be on Bright Talk on October 24th. If I don't drop in, I will listen to the recording. As I said several times, this is really a unique way of looking at how simulation can be leveraged, and it can have some significant impact compared to some of the things we do in the Ansys tool. So do check that out and give it a try. Let's take a break for a commercial, talk about our simulation services group, and that's consulting from PADT. And in the news section, we've got some important news in this area that we'll talk about.
Dave, you know that sending simulation work outside can be very difficult.
I sure do, Linda. It's so hard to find someone that knows how to conduct simulation that also understands our products and design needs enough to add value. How do you know you have the right partner?
You are so right. That is why so many companies turn to PADT for their engineering simulation needs. They are experts in structural, fluid flow, thermal, and electromagnetic simulation. They know how to drive design with simulation because PADT has been doing it for over 23 years. And some of their staff members have been building and running models for over 30 years.
That's a lot of experience. But let's be honest, working with a lot of outside providers is like throwing your projects over a wall. You send it, wait, and then get a number and a bill. That isn't what most people need.
You hit on a key difference with PADT's team and why they have been doing this for so long. They have the technology down, but they also know from experience that constant and smart communication with customers is critical. And when they get done, instead of delivering just a number and pretty plots, they provide insight into the physics and behavior of what they're modeling. It really is like having a group of experts right there on your team.
That is comforting. You can get burned without that. So I know I'm being kind of a skeptic, but simulation can be expensive and budgets are tight. So I want to make sure they really are a good solution. My last question is, how on earth do they stay so up to date on so many things?
Yes, their capabilities are kind of overwhelming in breadth and depth, but the answer is pretty simple. Besides doing simulation as a service, they are an Ansys Elite channel partner. They have to sell to and support over 100 customers. This gives them exposure to every Ansys product and almost every industry and application. You really can't find that anywhere else.
Okay, Linda, you convinced me. If someone needs to get some simulation done, how do they get started?
Easy. They can email info@padtinc.com, call 1-800-293-PADT, or visit www.padtinc.com/simulation. Someone from their engineering team will get back to them, usually within a day, to talk about what you need done.
Cool. Thanks, Linda.
Anytime. So what are you working on anyway?
All right, welcome back. Let's take a look at the Ansys stock. It almost hit $230 per share. It peaked at $229.20, I think, on Tuesday, October 15th. It's gone down a chunk since then. It's gone from that high of $229 down to $218.48. That's at the close of the market on the 18th. It's the 19th today. I looked in the news to see if I could detect why this was going on. Why did they have a big, not a big, but a drop, which we haven't seen in a while. And I have no idea. The earnings report for Ansys for the third quarter is coming out on the 6th of November, which is not that far away. So maybe that has something to do with it. Maybe, I don't know, people are selling before it comes out. I don't know. I don't understand it. I have no idea. Just know that the stock is down a little bit, but still very high. In fact, it's up 58.7% for the year to date, whereas the S&P 500 is only up 21.99%. So that's really good news. And again, that's all for the close of the market on the 18th. In Ansys news, there's a couple press releases on the Ansys news website. It's mostly about customers being very happy with Ansys and announcing partnerships and things. I found the one that talked about Richard Childress Racing, which is a NASCAR racing company, I guess. They make cars and motors and stuff. They've had a partnership with Ansys for some time. They've renewed it, and there's some interesting information in there about how they're getting better speeds and reliability on the track using Ansys tools. So I always thought that was kind of an interesting topic. There's also a press release about a company called TurboTech that is making hybrid electric, non-electric airplanes. And they're using Ansys to optimize their electric motors and such. So it's a pretty cool application. Someday we may all be flying around in electric cars, or, well, hopefully electric cars that fly, but maybe driving our electric car to the airport to fly in an electric airplane. There's also one from Samsung, which I think is pretty significant if you're on the electronic side of things. What they did is they certified Ansys Multiphysics to do multi-die packaging. So packaging is kind of how you put the chips on printed circuit boards, and you have solder and leads and all these things. It can be a really complicated simulation to do, and they talk about how they did that, which is pretty cool. That's pretty much it for the Ansys news. PADT-wise, it is official. We have some news to share with you from our consulting side of the business. We have a gentleman named Jeff Wells who has joined PADT in the engineering services department, heading up our business development for that department. So he'll be the person you contact for design, test, and simulation consulting. And he's a great person. A lot of people here in Arizona know him from his previous job, and a lot of our customers worked with him there before. So we're really happy to have him on board. He's getting up to speed and learning all of our lingo and everything right now. I know all of you who do consulting with us will enjoy working with him, and we're great and happy to have him on board. Publication-wise, the 3 articles that are worth note in the Ansys blog, there's quite a few in there. You should check it out. I just picked 3. The first one was What is Crosstalk? Electromagnetic Challenges and Trends in Electronics. So we see this a lot with our customers. We've been adding new customers and adding seats at customers who are dealing with this idea of crosstalk, which is that 2 circuits that are near to each other kind of leak into each other, and you get one signal from one to leak into the signal on the other, and it causes problems. And so you want to design around that, get rid of it. You want to know how bad it is, and then get rid of it. So they use Ansys tools to do that. So this kind of explains how that works. There's also a really good article about a new thing called distributed compute services, and it's a tool for basically running a bunch of Ansys jobs to do optimization. And it's called How to Use Distributed Computing to Speed Up Product Development. So DCS is Distributed Computing Services. Check that out. I'm not going to read the whole article to you on the podcast, so check it out. I found it really interesting. If you're not doing a lot of distributed computing, you should know that it's there in case you need it someday. And then finally, I'm a sucker for these articles from the Optus folks doing the very, very sophisticated, realistic renderings, ray tracings. They have an article called Visual Simulation and VR Help Optimize HMIs to Every Driver's Vision. So I had to look at what an HMI was, and that's the human-machine interface. It's the dials, the lights, the special indicators that tell you something's going on with your car. It's your dashboard, basically. And they point out the fact that because of age or glare or maybe color blindness, you don't really know what that looks like to other people. So you can use a tool to say, this is a 70-year-old person with cataracts, or there's really bad glare from the sun here. Can a colorblind person differentiate what this indicator, check engine light, looks like? So check that out. It was really interesting. I found it really cool. On our blog, Ted Harris put out an article called Ansys Mechanical: Overcoming Convergence Difficulties with the Semi-Implicit Method. So he basically took like a 2-liter Coke bottle and pushed on the top of it until it buckled and kind of caved in on itself. So that normally, as soon as it starts to buckle, we would have had a non-convergence and the model would have crashed. So now you can use this semi-implicit method to get through those large deformation buckling areas. It's got a really cool animation at the bottom as well of the bottle kind of crumpling. So check that one out from Ted. And upcoming events. We've got a webinar that we just talked about, predicting and controlling pollution out there. So do take a look at that one and register for it, or listen to it after it's been recorded and released. And that's on brighttalk.com, or you can go to our event page on our website at padtinc.com. Event-wise, we're going to the 2019 Governor's Celebration of Innovation next month. So, or not next month. It's late. Next week. So this is our annual gala here in town in Phoenix, where everybody in the tech world kind of shows up, and we give out awards. PADT makes the awards, so we like the awards. They're pretty cool, and they're going to look really cool this year. I'm really excited about those. So that event is going to be, I'm looking it up right now, on the 24th. So check that out. 4 o'clock to 8:30 if you're here in Phoenix. It's a fun event. Anybody in tech is there. So that's going to be Thursday the 24th down at the Convention Center in downtown Phoenix. And then later in the month, we head down to Tucson for the other annual event that we love, which is the 2019 Southern Arizona Tech and Business Expo. And we have a lot of Ansys customers down there in Tucson, so we hope you stop by the booth and say hi. That's going to be on the 30th, which is a Wednesday, and we'll be there from 12 to 6, just talking to people and enjoying the event. Then, just so you know, we'll be at the 2019 Fuel Cell Seminar and Energy Expo in Long Beach, and that's on the 5th and 7th through the 7th of November. I'm looking forward to that. And then next month's webinar is going to be on Flonex, so secondary air system modeling in Flonex. So we'll share more information about that when it becomes available. And that's it for our events, and that's it for the podcast. So thank you for listening. Don't forget to subscribe to www.padtinc.com/opt-in. You get all of our emails and our newsletter, which just went out. Spread the word, let people know what's going on, and that they can listen to this podcast, and don't hesitate to reach out. So thank you very much for listening, and I'm excited to see you at episode number 50. Thank you for joining us for the All Things Ansys podcast, episode number 49. As a reminder, this podcast is not affiliated in any way with Ansys Inc., and the opinions expressed are those of the people on the show only and not of their current or former employers. For more information, visit www.padtinc.com/blog, and please share your thoughts and questions through an email to podcast@padtinc.com. See you next time.